we need to determine the capacity of plate girder with reduced flange area again. Because what we will do after determining the capacity of plate girder with reduced flange area, we need to compare that capacity against bending moment diagram. So at what point the beam is or the plate girder is subjected to the bending moment same as of capacity of plate girder. So for the capacity of the plate girder, I will always suggest the student write down the equation. So if you are writing this equation, so this is the capacity of plate girder with reference to compression flange. So in this equation, what is required? We need to determine FCR value. So FCR value is based on lateral torsion buckling and flange local buckling. So we need to use the formula accordingly. RPG value we need to determine, that is the flexural strength reduction factor due to thin web, and we need to determine the section modulus of our plate girder with reference to compression flange. Okay, let's first of all we will determine the RPG value. So RPG value will be determined by the same formula that we have already discussed. You don't need to memorize this formula because this formula is given in LRFD design aid. So RPG, we need to know what is the AW value. So AW is the ratio of the web area to the flange area. Web area is 2300 into 10, and flange area, reduced flange area, here you need to substitute the values 500 into 18. So AW is 2.56. So this value is less than 10. So in this expression, you will substitute the AW value, height of the web over thickness of the web, and E over Fy value. So when you are computing the RPG value, the answer is 0.91. In the same way, you will compute section modulus. So section modulus is its moment of inertia divided by distance from the neutral axis to the extreme fiber. So I have already explained. So this is an expression. So you can also determine the moment of inertia by parts. You can consider the top flange and bottom flange area 1 and area 2 and web as a area 3. So moment of inertia of the cross section is determined by this expression that I already discussed and divided by the y value. So I have already discussed. So y value is h plus 2tf divided by 2. Distance from neutral axis to the extreme fiber. And here in this way, you can determine the section modulus with reference to compression flange. And you need to mention in experiment 3, 29,382. So only one thing is left, FCR value. So FCR value is either based upon flange local buckling or web local buckling. So I will show you the expression. Then I will come back how we can determine this value just to revise the concept here. So we need to determine the one FCR value based upon lateral torsion buckling and one FCR value based upon flange buckling. And the lesser value out of these two cases will be our desired value. So based upon lateral torsion buckling, we need to use any one expression. So maybe we need to use either this expression. If LB is less than LP, so then FCR value will be equal to Fy. And if our unbraced length is more than LP but less than LR, then we need to determine the FCR value by using this expression. And if LB is more than LR, then we have to use this expression. And based upon flange local buckling, if lambda F is less than lambda P, FCR will be equal to Fy. And if lambda F is more than lambda P and lambda R, then we need to determine the FCR value by this expression. This formula will not be applicable. Why? Because we never allow lambda more than lambda r. So we shall determine one FCR value based on later torsional buckling and one from plan local buckling. Okay, here you need to note down we are having CB value in this expression here also, but we do not have any FCR value, CB value over here. Why? Because we have already discussed CB value is the movement carrying capacity enhancement factor for later torsion buckling only. So this is the capacity modification factor for later torsion buckling. So CB value will only be used to increase capacity for later torsion buckling, not with reference to line of the buckling. So this formula and this formula is where we are having the LB, we are using lambda F, and where we are having LP, we are having lambda P, and where we are having LR, we are having lambda R value. So it means that we already know the LB and LB value. We just need to determine LP and LR value. So how we can determine LP, LR, we have already discussed. So we are having this expression for LP and LR. LP is 0.0311 time of RT and LR is 0.1062 RT. It means that if we want to determine LP and LR value, we need the RT value. So RT value will be determined by this expression. So what is RT value? That is radius of gyration of compression flange plus 1 by third of compression web. So this expression is already given in LRFD design aid, and so I have already explained in my classes. So you shall determine RT value by substituting thickness of flange and width of the flange value here with reduced flange area, okay? And similarly, you will substitute the area of the web and area of the flange. So RT value is 121. So when we are computing the LP and LR value for reduced flange area, so LP is coming 3.76 and LR is 12.85. So here we need to determine the capacity with reference to all sections. So for our inner portion, central portion, so here actually this value is 7. Why 7? Because I'm assuming that I can only reduce the flange area to half only in this end zone. So the central zone is subjected to maximum bending moment. So minimum moment within the central zone is 8749 and maximum moment is 9095. It means that I can only reduce the flange area to half only within this end zone. So it means that at the edges and in this end zone, this will be the zone where I am providing the flange with half area. So it means that the capacity of the plate girder will be checked only for the zone A and B, and also for zone C and D, because our plate girder is having identical loading and symmetrical bending diagram. So within this zone, I need to check the capacity. So LB of this edge zone is 7 meters. So LP value is 3.76 and LB is 7 meter. So LB is more than LP but less than LR. This means that our plate girder section with half flange area is non-compact with reference to lateral torsion buckling. So it means that FCR value based on lateral torsion buckling will be determined by this formula. So CB value Fy into 1 minus 0.03 LB minus LP and LR minus LP. So CB value we have already determined in our previous lecture for end segment, for segment AB. So I need to show you again. So, for portion AB and CD, we have already determined CB value, which was 1.57. When we determine the capacity with full flange area. So CB value we have already determined 1.57 for segment for portion AB and CD. So that's why when I'm substituting in this equation, Fy 250, LB 7, LP value, LR value 12.85. So I'm having the answer 350.53. So FCR value cannot be more than Fy. Similarly, just like we have discussed, moment carrying capacity cannot be more than MP. So the failure stress cannot be more than Fy. So we are keeping the FCR value equal to Fy based upon later torsion. Okay, now we will check with the reference of line local buckling. So lambda F value is 13.9 and lambda P is 10.8 and lambda R is 19. So how come I'm getting this value 13.9? Because I have determined over here. This means that our flange is also non-compact with reference to line local buckling. So I will determine the FCR value based upon line local buckling by using this formula. And in this formula, we are not having any CB value. Why we are not having CB value over here? Because I told you CB value is only used against lateral torsion buckling. So this formula is giving the answer less than Fy 221.08. So we are having two FCR value, 1 250 based upon lateral torsion buckling and 1 221.08 based upon plan local buckling. So lesser value will be used in the equation, which is 221.08. So in this equation, we need to substitute the value 5B.9 section modulus with reference to compression plan. So please correct it. There might be some mistake. So I need to verify this. Anyhow, I will check it later. Or maybe you need to check this answer. The answer should be the same. Let me check if I have copied from my previous slide or not. Okay, anyhow, I will check this answer maybe by mistake. This value must be 29. So anyhow, RPG value 0.91 and FCR value 221.08. So the capacity is 5320. And that's what we need to do. Capacity is 5320. We need to check in this beam. From the end, bending moment diagram is increasing from 0 to 1000, 2, 3, 4, 5, 6, 7, 8000, and up to 9095 in the center. So we need to check the location here at the end span from within AB and CD. At what point the applied bending moment is exactly equal to capacity of plate girder with half length. Or I need to determine the location where applied bending moment is exactly equal to 5320. So it means that I can write down the equation for this central zone. If I'm assuming the cutting section here, and I will write the equation 1519x minus 76.9 x squared by 2 and equate to the moment so I can determine the location. So I'm interested to determine the location where the moment is equal to 5320. So how I can do? So we have written this equation. So let me further uh, so this equation actually this is derived by this concept. So we can say that this equation is written by Bmn should be equal to mx or moment in the beam. So we are comparing this. So this is 5Bmn and this is the moment equation 1519x minus 76.9x squared by 2. So I'm using this equation. So in this equation, this will be a quadratic equation in term of x because I am bringing the x to the other side or dividing this equation by 2. So this equation will have two roots. So one root will be 3.9. It means that 3.9 is the location at which the moment applied moment is equal to 5320, which is exactly equal to the capacity of plate girder with half flange area. So it means that at that point I can reduce the flange area to half. So I will show you the diagram how I can calculate this plate girder or can reduce the flange area to half along the length. So next is the design of the weld. So you are already familiar, maybe in the beam topic we have discussed. So plate girder is subjected to, or beam is subjected to shear stresses. So there was one diagram. Yes, here. So in plate girder, we need to actually this web is a separate plate and flange is a separate plate. So we need to provide the weld over here. So actually, this weld will be designed for a shear force. And what shear force? This shear stresses which are produced over here. Because you know that shear stresses you can compute by the formula VAY over IB. So this is the shear force which is produced due to applied force at the junction. And this shear force, if we are not connecting the flange with the web, so the flange and web they can slide. So we need to weld it over here. So the weld strength should be such that, or the shear strength of this weld should be more than this shear stress, so that the sliding may not occur, and plate girder it may behave as a composite section or as an integral section. So flange and the web they can bend together. So we need to determine what are the shear stresses at this point. So you can determine this shear stresses by the formula VAY over IB. So which is being determined over here. So the last time I guess that I have also explained, but let me re-explain. Which formula we are using actually. So actually we are using this formula. Tau is equal to VQ over IB. So here this IB will be our thickness, or Q is, you can compute separately, AY partial area, static moment of area, because we want to compute these stresses at this point. So partial moment of the area of flange, or area which is above the layer, and that's moment arm. So, and B will be equal to thickness of web, and moment of inertia will be equal to Ix. And moment of inertia of entire cross section. So partial area which is the area of the flange, and distance from the centroid of the partial area to the neutral axis. So we shall use this formula to determine shear stresses. So I'm just mentioning this formula over here. So, so we are computing the Q value separately. So Q, we are having partial area of the flange only. So area of the flange 500 into 18, and distance from the center of the flange to the neutral axis will be H plus, or H by 2 plus TF by 2, or H plus TF by 2, distance from the center of the flange to the neutral axis. So there is another way. Actually, we are using the concept of shear flow rather than shear stresses. So here, this shear stresses that we have already determined. So actually, we want to use the concept of shear flow if we are multiplying this Q value with the thickness of the layer, which is equal to Q into PW, or with the B value. And or what we are doing, we are removing this thickness. So then shear stress can be converted into force acting per unit length. So we are interested to determine shear flow rather than shear stresses. Why? Because their units will be equal to kilonewton per meter. So this topic you will study in detail in your next semester. Actually, for the thin walled section like steel structure, where the thickness of the element is very small. So instead of representing the stress, we are representing as a force acting per unit length. And we are assuming that the stress, they are uniformly distributed along the thickness. So why we are determining shear flow in kilonewton per meter? Because we need to compare with the weld value. So weld value is also force acting per unit length. So instead of shear stress, we want to convert into shear flow, which is if we are multiplying the stress with the thickness, just like I'm bringing the thickness to the other side, so that will become shear flow. And the units will be kilonewton and meter. So let me write here, that is kilonewton per meter. It means that that is the total shear flow or force acting per unit length acting at the junction here. So actually we are welding on the both sides. So it means that our weld should resist this shear flow. So one weld is resisting half shear flow and two welds they will resist the total shear flow. So shear flow will be 0.462 kilonewton per millimeter. So actually, sorry, this answer will be in kilonewton per millimeter because we are using the dimension in millimeter. And this dimension will also be millimeter. So I need to further reduce it. Okay, next we want to determine the thickness of the weld. So first let me. So we are connecting web with the flange. So thickness of the flange is 28 mm in center and 18 mm at the edges. And thickness of the web is 10 mm. So you are already familiar with weld design. So TP1 will be our thickness of the web 10 mm because we want to connect two plates, and TP2 will be either 18 or 28. So let's suppose at the edges we are using 18 mm for thickness of flange. So TW minimum is 5 millimeter because if TP1 is between 6 to 13 mm, then TW minimum is 5. And if TP1 is more than 6 mm, then TW maximum is equal to TP1 minus 2, so which is 8. 10 minus 2 is equal to 8, and T optimum is also 8. So we arrange all the three thicknesses in ascending or descending order, and middle one. So middle one value, this is also 8 and this is 8. So we are opting the thickness of the web as thickness of the weld as 8 mm. And let's suppose we are using E70 electrode. So we can determine the weld value based upon shear strength of the weld or shear and rupture of base metal. So 0.75 is the phi value, 8 is the thickness of weld. This is a factor to convert the thickness of the weld into effective slot. Length of the weld we are using as a 1, and zero point 0.6 is used a factor to convert the tensile strength to the shear strength. So weld value based on shear strength of the weld is 1.26, and weld value based upon rupture of or the shear rupture of base metal is 1.8. 0.75 is phi value, 10 is AP1 unit length, and zero point 0.6 is the factor to convert the ultimate strength 430 60 400 FU to shear. So the lesser value is 1.26. Okay, here I need to explain another way. Actually, if we are welding the plate girder throughout the length, so our plate girder will be highly uneconomical. So instead of welding thoroughly, we are providing the intermittent weld. So how we can provide the intermittent weld? So here I'm going to explain. So actually our formula is this one. Fu, sorry, length of weld is equal to Fu divided by weld value that we discussed many times in our lab classes. But here reason is that Fu is in kilonewton. So there is a one issue. So what we can do, we are having actually another expression. We are having shear flow. So shear flow is force acting per unit length. So it means that if I'm dividing the Fu by X value, any unknown value, then this value will be equal to shear flow. And the units will be in kilonewton per meter. Or from here, what I can say that I need to substitute the Fu value in terms of Q dot X because we are not having the Fu value, rather we are having shear flow. So we have to use this formula. So, so our formula will become Q dot X. Okay, what we are doing and why I have explained this. So what we will do, we will provide the intermittent weld along the length. I will explain. And intermittent weld will be provided corresponding to LW minimum. So LW minimum is 4 times of thickness of the weld we have already discussed, which is 32. So we will round to the this weld to the upper side. So minimum weld length may be provided as at 32. So let's suppose we are providing the weld equal to 50 mm. So length of the weld we have already fixed. So we need to determine the X value. So X value is the center to center distance between the intermittent weld or pitch of the weld that we have determined by the concept of shear flow. Because if shear flow is multiplied with the X value, so that value will be equal to Fu. So it means that this shear flow is being resisted by this X value, which is center to center distance between that. And how come I have computed this X value? I have explained. So in this equation, length of the weld we have fixed just more than LW minimum 50 mm. So LW is known, Q value is known, weld value is known, so only unknown is X value. So X value, so the formula will become like this. So X value we can determine, so X value will be equal to length of the weld into the weld value divided by Q. So after substituting the values, we are having the X value 2.7. So this is the pitch of the weld. So the maximum center to center distance between the weld we can kept as a 272. So we will round this value to the lower side, maybe in a multiple of 25 mm. So we can use X value, any value less than this value. So to bring this value in the safe limit, so we are using the length x value, or the center to center distance between the weld is 250. So we are using the weld 8 mm thick, length of the weld 50 millimeter, and having center to center distance 250 along the length. So this is the weld we are going to provide. So how this weld will be provided, and I will explain. Okay, first of all, this is the diagram or the plan view or and the front view of plate girder. So we are having plate girder dimension in the center. In the center, we are having the maximum bending moment. So in center, we are providing the plate girder like this. This is top view. So the width of the flange will be 600 in the center, and the thickness of the flange will be 28 millimeter. Actually, this is the theoretical location or theoretical cutoff point, which is at a distance 3.9 meter from this edge, and also from 3.9 meter from the other edge. So at this point, we can reduce the flange area to half, or where the half flange area is having the capacity equal to mu. But we are not abruptly or suddenly reducing the flange area to half at this theoretical location. Rather, what we will do, we are using a safe margin or a safe cutoff point. So we actually reduce the flange area to half at a distance around 200 millimeter or around maybe 8 inches. So this could be 100 millimeter, but normally in drawings, this distance is kept around 8 inches or 200 millimeter. So what we do, we mark another point at a distance of 200 millimeter from theoretical cutoff point. So this will be regarded as an actual cutoff point. So within this zone, we are having flange dimension 500 millimeter corresponding to half flange area and thickness of the flange 18 mm. So here in this edge zone, we are having thickness of the flange 18 mm and width 500, and then we reduce flange area gradually from theoretical cutoff point to the actual cutoff point. So we reduce the full flange thickness from 828 to 18 mm, and similarly we reduce the flange width from 600 mm to 500 mm at actual cutoff point. So this is a separate plate, and this flange plate is a separate plate. So we cut or reduce the larger plate to match with this smaller plate. So at this point, the both plates, they are being welded with groove weld. So weld is provided throughout the thickness. So a solid weld is provided at actual cutoff point. Okay, next, how we can provide the intermittent weld. So let me copy, duplicate this slide, and I will show you how we provide this weld. Can I copy this one? Okay, okay. This is just may not be the. So we provide the intermittent weld. For example, one weld will be provided here. Maybe let me reduce the thickness further so that it looks intermittent. So So these are the intermittent welds which are provided at the junction of top flange to the bottom flange, and we keep the center to center distance as 250 mm. So this is how we provide the weld. So intermittent weld is provided on the both sides and also to the bottom side. So center to center distance between these intermittent weld is kept as 250. So I will set them later on. So center to center distance between these weld is kept as 250. So 250. So you need to show this weld with proper designation, just like you have used in for your member weld design for the member. So this will be 8 into 50 at 250. So you can use this definition. So here I will conclude my lecture. So next time I will start the design for the bearing stiffener. So please raise the hand, all the students who are present. So where is Farhan? Ayan?
Yes, sir, Farhan.
Okay. Haris? Haris? Saleha Nain? Shehbaz?
Sir, I'm here. My internet was not working.
Okay. And Shahzeब Hamid and Haris Chaudhary. यार इनको दोनों को नोट करो, इनको रोल नंबर सेंड करो मुझे हैं हारिस चौधरी एंड शाहजेब हमीद. ठीक है.
Okay, sir.
Okay, I have only maybe 1 to 1 hour to 30 minutes
सर
instruction.
शाहजेब
ठीक है. ओके
इंटरनेट का मसला
यार, तो इंटरनेट का मसला तो रेज हैंड नहीं हो रहा आपका.
नहीं हो रहा
ओके. हारिस चौधरी, तो ठीक है, फिर तब आपके चैनल को आंसर करता हूँ. ठीक है. So I only require maybe 1 hour or maybe 1 hour and 30 minutes to give you the instruction regarding the steel design sheet. So I believe that maybe in the next week I will have the lab session. So today there will be no lab class as well. So maybe in the next week I will give you the instruction regarding the selection of the member for the truss and how you can sketch the truss design sheet. So if someone is having any question regarding today's lecture, he can ask me. Otherwise, I will conclude the lecture.